Module 5, Lecture A, Robust Engineering Scripts. By the end of this lecture, you will be able to validate user inputs to prevent invalid electrical quantities from corrupting calculations, use exception handling to manage conversion errors, missing files, and impossible operations, and create simple test cases that confirm engineering functions return expected results. Input validation. Parameter checks. Parameter checks help engineering scripts use inputs correctly and avoid misleading results. Before calculations begin, the script should confirm that each input exists, is numeric, has the right format, and represents the intended electrical quantity, such as resistance or voltage. Parameter checks help catch errors before calculations begin by verifying units, data types, and missing or malformed values. For example, voltage values may be recorded in different units, or imported data may contain blanks or incorrect formats. Checking these fields early ensures values such as voltage and current are usable and correctly formatted, preventing mistakes from spreading through the script. Parameter checks help engineering scripts catch bad or missing inputs before they affect calculations, reports, or equipment settings. If required data such as cable length or resistance information is unclear or incorrect, the script should stop and request clarification instead of continuing with unreliable results. These checks do not replace professional review, but they reduce the chance that input errors will influence technical decisions. Python code, parameter checks. Parameter checks help protect engineering calculations by making sure electrical values are meaningful numbers. Invalid inputs should be caught early so errors do not spread through the calculation. Unit conversion mappings are defined so inputs can be converted into standard base units for calculation. Voltage is standardized to volts, with kilovolts treated as 1000 volts. Current is standardized to amperes, with milliamperes treated as 1,000th of an ampere. Length is standardized to meters, with feet converted using 0.3048 meters per foot. The function first tries to convert the input into a floating point number to confirm it can be used in calculations. If the value is missing, the wrong type, or cannot be converted, it raises a clear value error, saying the parameter must be numeric. This early validation prevents invalid input from causing problems later. The code validates inputs before running calculations. It first rejects any unrecognized unit, then checks whether the numeric value is below the allowed minimum. If either check fails, it raises an error, helping prevent invalid or unsafe engineering calculations. The code converts an input value into a standard unit by multiplying it by the matching conversion factor from the allowed units. It then returns the converted value, so the rest of the program can use consistent measurements. To calculate a simple single-phase load current, the load current function takes the voltage value, its unit, and the power in watts. It first checks the voltage using a validation function, which confirms that the value is numeric, uses an accepted unit, and is at least 1. This also converts the voltage into a consistent unit for the later calculation. First, the power value is checked to make sure it is numeric, measured in watts, and not negative. Then the load current is found by dividing the power by the voltage, giving the result in amperes. The test cases are organized as tuples that describe different voltage inputs and expected conditions. Each case includes a label, a voltage value, a voltage unit such as volts or kilovolts, and a fixed power value of 1150 watts. Together, these cases check both valid and invalid inputs, including wrong data types, negative values, and unsupported units. The process stores test results in an empty results list, then checks each test case using its label, voltage, unit, and power value. For each case, it tries to calculate the load current with the load current function. Successful calculations are recorded as accepted with the current in amps, while value errors are caught and recorded as rejected with the error message. Each outcome is added to the results list for later use. The code saves each test case result in a results list. This keeps track of whether the input produced a valid current calculation or was rejected as invalid. Later, the script can display a summary showing which cases passed or failed and why. The code goes through each stored result and prints it to the console. This gives a brief summary of each test case, showing whether the input was accepted or rejected, and including any related error messages. The checked quantity function validates a cable length entered as 30 meters. It confirms that the unit is allowed, the value is not below the minimum of 0, and the input can be converted into a consistent numeric form. If valid, it returns the cable length in meters. The checked quantity function is used to convert a cable length from feet to meters. It is given a label, the value 100, the unit feet, a set of length conversion factors, and a minimum value of 0 to prevent negative lengths. The function then returns the equivalent length in meters. The output verifies cable length conversions to meters. It confirms that 30 meters remains 30 meters, and that 100 feet is correctly converted to its meter value, demonstrating that the program's unit conversion works consistently. This script checks electrical calculation inputs before using them, making sure values are numeric and units are valid for voltage, current, and length. It calculates load current as power divided by voltage after validation, accepts correct test cases, and reports errors for invalid ones. It also converts cable lengths between metric and imperial units to confirm consistent unit handling. Overall, it shows how early validation and unit conversion improve reliability in engineering calculations. Acceptable value ranges. Engineering scripts should check that inputs are both the right type and realistic for the system. Values like negative resistance or an extremely high voltage may be numeric, but they can lead to invalid or misleading results. Setting acceptable ranges helps keep calculations practical and protects the workflow from unrealistic assumptions. Engineering scripts often need acceptable value ranges based on component limits, manufacturer ratings, and design context. These ranges help flag unsafe current, abnormal battery voltage, or sensor readings outside calibration before they affect control decisions. By embedding this domain knowledge, the script becomes a smarter tool rather than just a calculator. Acceptable value ranges make automation scripts more reliable by checking that inputs stay within expected limits. When an input is rejected, the script should clearly explain whether the problem is a typo, wrong unit, or possible system fault. These checks prevent bad calculations and help catch errors or abnormal conditions early before they affect reports or automated actions. Python code. Acceptable value ranges. Validate input values before performing electrical calculations. Range limits reflect expected engineering constraints, and rejecting invalid inputs helps protect downstream automation from errors. We define safe input ranges for basic electrical calculations. Voltage from 0 to 24 volts, resistance from 1 to 10,000 ohms, and current from 0 to 2 amperes. These limits help validate values before calculation and keep results within expected engineering and safety standards. A list of sensor readings stores each sensor's name, voltage, and resistance together. This structure makes it easy to process each sensor's data, such as checking values and calculating current. This function determines whether a value is within a given range. It receives the value in a pair of bounds, then checks whether the value is at least the lower limit and at most the upper limit. The result is true when the value falls inside the range and false otherwise. The safe current function calculates electrical current only after confirming that the inputs are safe. It checks whether the voltage and resistance fall within their allowed ranges, and raises an error if either value is invalid. It then calculates current as voltage divided by resistance, checks that the result stays within the project limit, and returns the current only as all checks pass. The process separates readings into accepted and rejected groups. Each reading is checked by using the safe current function to calculate current from its voltage and resistance. Valid readings are saved with their calculated current, while readings that raise a value error are saved with the error message. This keeps valid data ready for further use and records invalid data clearly. The program prints a short heading for the accepted sensor readings, then goes through each valid sensor entry. For every sensor, it displays the sensor name and its current value in amperes, rounded to 4 decimal places. This gives a concise summary of the readings that passed validation. The output begins with a short heading for rejected readings, then reports each rejected sensor reading with its reason. This makes it easy to see which readings failed validation and helps identify problems in the input data or validation process. A simple test confirms the code behaves as expected. It checks that calculating current from 10 volts and 1000 ohms gives approximately 0.01, allowing for tiny floating point error. It also verifies that 1 reading is accepted and 3 are rejected. If all checks pass, the test prints a message confirming the range validation works correctly. This script checks sensor readings against safe engineering limits for voltage, resistance, and calculated current. Readings outside the allowed ranges are rejected with clear error messages, while valid readings are accepted and their current values are shown. In the example run, 1 reading passes and 3 fail for specific reasons. Assertions at the end confirm that the validation and calculations behave correctly, helping prevent invalid data from reaching later processing steps. Range validation. Range validation checks that engineering values are not only the right type and unit, but also within safe and meaningful limits. This helps prevent calculations based on unsuitable inputs, such as values that exceed equipment ratings. By adding engineering judgment to scripts, range validation reduces misleading results, unsafe recommendations, and wasted troubleshooting time. To validate electrical ranges, choose realistic limits for each quantity and decide how strictly to enforce them. Some limits come from physical rules, such as rejecting negative resistance or frequency, while others depend on equipment ratings and the specific application. The goal is to match the accepted range to the system being modeled and to the risk of letting unlikely values affect the calculations. Range validation helps scripts catch input mistakes early before they produce misleading results. For example, it can detect when a value is entered in the wrong unit, such as milliohms instead of ohms. This makes scripts more reliable in collaborative engineering work, where data may come from many sources. Checking ranges up front helps users distinguish real system issues from simple data entry errors. Python code. Range validation. Range checks help protect engineering calculations by catching invalid values early. Clear error messages make scripts more reliable and easier to troubleshoot. Set the voltage range from 0 to 600 volts. These limits define the acceptable minimum and maximum values, helping keep later engineering calculations safe, consistent, and reliable. Resistance values are limited to a safe, realistic range from 0.1 ohms to 10,000 ohms. The lower limit helps avoid division by zero, while the upper limit prevents impractical or unsafe values. Together, these boundaries support reliable resistance calculations. The validate range function checks whether a numeric value is within an allowed lower and upper limit. It uses the quantity name, the value, and the two bounds, then accepts the value only if it falls within that inclusive range. This helps catch invalid inputs early, before they are used in further calculations. The code creates a clear validation error message using the input's name, its actual value, and the allowed range. It then raises a value error to stop the program and tell the user exactly what is wrong with the input. The function calculates power only after confirming the inputs are valid. It first checks that the voltage falls within the allowed range, using the validate range function. This helps prevent errors before the calculation continues. Before any division is performed, the script validates that the resistance is within the allowed minimum and maximum limits. A checking function returns the resistance if it is valid, or raises a clear error if it is not. This prevents invalid calculations and helps keep the script reliable. This calculation uses Ohm's law to find power. It squares the voltage and divides by the resistance, producing the power in watts as the function's result. A set of test cases is created to check a power calculation function using different voltage and resistance values. The cases include typical valid inputs, one voltage value outside the allowed range to test error handling, and one very small resistance value near the valid edge. Together, they help confirm that the function works correctly for normal, boundary, and invalid inputs. The code tests several voltage and resistance pairs by using the calculate power function. When the inputs are valid, it prints the voltage, resistance, and power rounded to one decimal place. If an input is outside the allowed range, it catches the value error and reports that the calculation was rejected. The test sets an expected power of 60 watts, then uses the power calculation function with 120 volts and 240 ohms. The function checks that the inputs are within allowed limits and computes power using Ohm's law. The calculated result is then compared with the expected value to confirm that the function works correctly. The code verifies the calculation by comparing the computed power with an expected value. If their absolute difference is smaller than a tiny tolerance, the values are treated as equal, and a message reports whether the test passed. This script demonstrates defensive programming for an Ohm's law power calculation. It checks that voltage and resistance stay within allowed ranges before computing power as voltage squared divided by resistance. Valid inputs produce results, while invalid inputs are rejected with clear error messages. It also confirms one expected result with a test case. Error handling. Exception handling. Exception handling lets a script respond in a controlled way when data cannot be processed normally. In engineering automation, this is important because user inputs and measurements often drive design decisions, and errors like wrong units or stray letters can stop calculations or mislead users. Good error handling explains problems clearly, prevents bad data from entering calculations, and makes scripts more reliable. A good exception handling strategy separates predictable user mistakes from failures that suggest deeper problems. Expected errors such as invalid input or unsupported units should be handled smoothly by guiding the user or recording the issue. But if valid input still causes a failure, it may point to a script defect that needs investigation. Precise exception handling helps users correct routine problems while making serious issues easier to detect. Exception handling helps engineering scripts stay reliable when used repeatedly by many people. If data cannot be converted because of a symbol or formatting problem, the script should not silently ignore it or replace it with a default value. It should stop that operation, report the issue clearly, and allow the user to correct the data. This protects quality control and keeps automation dependable when real-world data is imperfect. Python code, exception handling. Use exception handling to protect engineering calculations from invalid input data. By catching specific errors, bad values can be handled safely without corrupting later results, and script failures become easier to understand and fix. A sample list of resistance measurements is created to represent field data with mixed quality. It includes both valid numeric values and an invalid text entry, showing the kinds of input problems that can occur in engineering work. This setup helps demonstrate how later code can process data robustly and handle invalid entries. The function converts the voltage and resistance inputs from text into floating point numbers so they can be used in calculations. Because the inputs may not be valid numbers, the conversion is placed in a try block. This helps the program handle unexpected input without failing abruptly. The code checks that the resistance is greater than 0 before calculating power. If the value is 0 or negative, it raises a zero division error with a clear message. This prevents an undefined calculation and lets the program handle the problem safely instead of crashing unexpectedly. The code computes electrical power by squaring the voltage and dividing the result by the resistance. It then rounds the power value to 2 decimal places so the output is precise and easy to read. This code handles invalid number inputs safely. If the voltage or resistance text cannot be converted to a floating point number, the error is caught and a conversion error message is returned instead of crashing the program. This lets the program continue running gracefully when the user enters invalid input. This code catches a zero division error that can occur when the resistance value is 0 or negative during a power calculation. Instead of letting the program crash, it returns the error message as text. This helps the user understand what went wrong and makes debugging more reliable. The code first signals that exception handling results are about to be shown. This introduces how the program responds to errors during automation, especially when processing different resistance values that may trigger problems. The process checks each raw resistance value and uses the safe power function with a fixed voltage of 24 to calculate power. This function handles conversion or calculation errors, so invalid resistance values do not stop the workflow. Each output, whether a power value or an error message, is saved for later use or display. The code displays each resistance value along with its calculated power result in a formatted message. By embedding both values directly in the output, it makes each loop iteration easy to follow and shows how the resistance affects the calculation. The program tries to open a missing configuration file in read mode using a with statement. This automatically closes the file when the operation finishes, even if an error occurs. If the file opens, its contents are stored for use, supporting graceful handling of possible file access problems. If the program tries to open a missing file, it catches the file not found error instead of crashing. It then uses a default message saying a default voltage limit will be applied, so the program can keep running normally. The code reports the result of checking for a configuration file. If the file were found, it would print its contents, but because it is missing, the code prints a default message instead. This confirms that the program falls back to a default setting when the file is unavailable. This example checks whether the safe power function gives the correct result for known inputs. Using a voltage of 24 and a resistance of 10, it calculates power as voltage squared divided by resistance, then compares the result with the expected value of 57.6. Matching these values confirms that the function behaves as intended. The code verifies that the safe power function returns the expected result. It compares the computed value with 57.6, and if they match, it prints that the test passed. This script shows how Python can handle errors during engineering calculations. It converts text resistance values into numbers, calculates power using a fixed voltage, and returns clear messages when inputs are invalid or resistance is 0. It also handles a missing configuration file by using a default message and checks one known result to confirm the calculation works correctly. Missing file handling. Engineering scripts should handle missing files safely because many tasks depend on external data. If a required file is not found, the script should stop and clearly tell the user what is missing, instead of continuing with incomplete or wrong information. Anticipating this common problem makes scripts more reliable and helps users correct issues with confidence. When a file is missing, first consider whether its location or name has changed, especially across different computers or networks. Exception handling helps a script catch this problem and respond with a useful message, such as identifying the expected file and suggesting checks for where it was generated or moved. This makes the program easier to use by guiding the user instead of showing a confusing error. Handle missing files with clear, deliberate choices. If missing data would make results unreliable, stop the script gracefully. Otherwise, use a safe default, skip the data, or ask for a new location. The script should never guess silently, and it should log these events so problems are easier to diagnose and maintain later. Python code, missing file handling. Engineering scripts often rely on external data, so missing files need to be handled clearly. This example shows how to use a safe fallback when required data is unavailable. The code imports the path class from the pathlib module to work with file paths reliably across operating systems. This makes path handling more consistent and reduces errors caused by different file system conventions. The script defines two file locations using a path handling library, one for the preferred load profile data and one for a default backup. This fallback setup helps the program keep running if the expected data file is missing. The script creates a small backup data file containing CSV-style hour and current readings. It writes this fallback data using UTF-8 encoding, so the program still has valid data to use if the main file is missing. The function first tries to read text from the specified file using UTF-8 encoding to handle characters correctly. If the read succeeds, it records the file's name as the source. This lets the function prioritize the main data file whenever it is available. This code handles a missing data file by catching the file not found error. When that happens, it records a message about the missing file, loads default data from a fallback file, and stores the fallback file as the actual source so the user knows what was used. If the file is read without errors, The function records that it loaded successfully. It then returns the file's text, the name of the file used, and a status message. This gives the rest of the script both the data and clear context about which file was accessed. The function cleans the CSV text, splits it into rows, and checks whether any measurement data exists beyond the header. If there are fewer than 2 rows, it raises an error to show that no data is available. This prevents the function from processing an invalid or empty dataset. The process creates an empty list to store current measurements, then reads each data row after the header. For each row, it separates the hour from the current value, converts the current value into a decimal number, and adds it to the list. This prepares the current data for later calculations. The function first checks whether any current values are available. If the list is empty, it raises an error to avoid dividing by 0. Otherwise, it returns the average by adding the currents and dividing by how many values there are. The script first tries to read the load profile from the preferred file, and if it is missing, it uses a backup file instead. It reports which file was loaded and whether the fallback was needed. The retrieved data is then parsed to extract current values and calculate their average. This shows how a fallback file helps the program keep running with reliable data. The script demonstrates how it handles a missing file by reporting whether the requested data was loaded or a fallback was used. It then shows the actual data source, prints the average feeder current to 2 decimal places, and confirms that the script continued using the documented fallback file. This script shows how to keep engineering data processing running when an expected load profile file is missing. It checks for the preferred CSV file, uses a default file if needed, then reads the data and calculates the average current. The output reports which data source was used and the resulting average, providing a clear fallback strategy for missing input files. Handling impossible operations. In engineering scripts, an impossible operation occurs when current conditions make a valid result impossible, even if the input appears acceptable. Examples include calculating resistance with 0 current or power with negative resistance, which can let a script continue with misleading results. Good error handling patches these cases early, stops the unsafe calculation, and explains the problem clearly so users can fix the cause. Handling impossible operations means recognizing both math limits and invalid engineering scenarios. Instead of simply blocking cases like dividing by 0, scripts should explain why an input does not make sense, such as a 0-hour battery load or transformer efficiency above 100%. Clear exception handling helps users identify bad assumptions or input errors and prevents invalid results from being treated as valid. Professional automation scripts should handle impossible or unsafe operations in a controlled way. By checking for problems such as division by 0, invalid negative values, or unrealistic inputs, the script can stop safely and give clear feedback. This makes errors easier to diagnose and helps users trust the tool. Python code, handling impossible operations. This script manages impossible electrical calculations by using exceptions to prevent unsafe operations. Small tests check that it behaves as expected for engineering use. This line means the script needs no extra Python packages. It relies only on Python's built-in features, so it can run without installing external libraries. The calculate resistance function finds electrical resistance from voltage and current, but first checks that the current is not zero. If the current is zero, it raises an error because division by zero is undefined. This prevents invalid calculations and ensures the function only runs with safe, meaningful input. This code checks whether the voltage is negative and raises an error if it is. This prevents the function from processing invalid input, since only non-negative voltage values are meaningful in this electrical context. This calculation uses Ohm's law to find resistance by dividing voltage by current. It assumes the inputs have already been checked, including that the current is not zero and the voltage is not negative. The calculate power function computes electrical power from current and resistance, but first checks that the resistance is valid. If the resistance is negative, it raises an error because negative resistance is physically impossible. This prevents invalid calculations and protects the correctness of the engineering logic. This calculation finds electrical power as current squared multiplied by resistance. It uses a standard electrical engineering relationship, assuming the current and resistance values have already been checked as valid earlier in the code. A scenarios list is used to organize engineering test cases in a consistent way. Each scenario includes a descriptive name, the function being tested, and the arguments passed to that function. The tests cover normal inputs, such as calculating resistance from voltage and current, as well as error cases like zero current or negative resistance. This structure makes it easier to run checks systematically and handle expected exceptions. The program goes through each scenario, separates out its name, the function to run, and the values to use, then executes the function safely. By using error handling, it can catch problems from invalid operations and keep the program running instead of stopping unexpectedly. The code runs a function with the provided inputs and reports the result for each scenario. If the operation succeeds, it prints the scenario name and the result rounded to 2 decimal places. If the operation is invalid and raises a value error, it catches the error and reports that the operation was blocked along with the error message. Initialize a pass counter at 0 to track successful checks. Then test the resistance calculation by using 24 volts and 6 amps, which should produce a resistance of 4. We validate the resistance calculation by checking whether its expected value is 4. If it matches, we add 1 to the count of past tests, helping track that the function behaves as expected under normal conditions. The test checks that the resistance calculation handles zero current correctly. When the function is given a voltage of 5 and a current of 0, it raises a value error instead of allowing division by 0. Catching this error counts as a pass test, confirming the invalid operation is properly blocked. The test checks that the calculate power function rejects a negative resistance value. It tries to run the calculation with a current of 2 and a resistance of -1, which should raise a value error. When that error is caught, the test is counted as passed because the function correctly handles an impossible resistance. The script ends by printing a short test summary. It formats the message to include how many of the 3 tests passed, giving a quick view of whether the script handled the expected scenarios correctly. This script shows how exceptions can prevent impossible electrical calculations. It calculates resistance and power only when the inputs are valid, and rejects cases such as zero current or negative resistance with error messages. It also runs tests for a valid calculation, division by 0, and negative resistance, and all tests pass, showing that the script handles these edge cases reliably. Basic function testing. Expected results. Expected results give engineers a simple benchmark for checking whether a function works correctly. Before using a script for design or troubleshooting, choose a few test inputs with known outputs from hand calculations or trusted tools. These quick checks are not meant to cover every case at first, but to confirm the function's basic behavior and catch obvious errors. Expected results for a function should be accurate enough to reveal errors, but still practical. In engineering scripts, small mistakes can produce results that look reasonable, so tests should use predictable cases such as standard appliance ratings for circuit load calculations. This helps catch problems like swapped units or rounding errors, and improves the reliability of calculations for power use or voltage drop. Expected results help engineers trust automation by showing when changes break existing behavior. As scripts grow more complex and connect to more inputs and workflows, simple tests with clear outcomes provide a safety net. If a previously correct function starts producing different results, it signals that the change needs investigation. This makes expected results a key practice for keeping automation accurate and reliable. Python code. Expected results. Basic tests check functions against known results, helping catch mistakes in engineering calculations. Starting with small examples builds confidence before moving on to automation. This function uses Ohm's law to calculate current by dividing voltage by resistance. It accepts voltage and resistance values, first checking that the resistance is positive. If the resistance is 0 or negative, it raises an error because that is not a valid physical value. Otherwise, it returns the current in amperes. This calculation uses Ohm's law to find current by dividing voltage by resistance. It assumes the resistance is positive as the function has already checked. This function computes electrical power from voltage and current. Before doing the calculation, it checks that both values are non-negative and raises an error if either one is negative, ensuring the inputs are valid for this context. This function calculates electrical power by multiplying voltage by current. It takes volts and amps as inputs and returns the power in watts, assuming the values have already been checked as valid and non-negative. A set of test cases is created to check the current calculation function. Each test includes a label, the function to run, its input values, and the expected output. Two examples use voltage and resistance pairs of 120 volts with 60 ohms and 24 volts with 12 ohms, both expecting 2 amperes. This makes it easy to verify that the function returns correct results for known inputs. Two new test cases are added to check the power calculation function. Each case identifies it as a power test, provides voltage and current inputs, and includes the expected wattage result. The examples use 12 volts with 3 amps to expect 36 watts, and 230 volts with half an amp to expect 115 watts. The test setup begins by setting the count of past tests to 0. And recording the total number of test cases. It also defines a very small tolerance, 1 times 10 to the negative 9, so calculated results can be compared with expected values while allowing for tiny numerical differences. Each test case provides a function, its inputs, and the expected result. The function is run with those inputs, and its output is compared to the expected value by measuring the absolute difference. This checks whether the result is close enough within the allowed tolerance. A test passes when the calculated value is close enough to the expected value, meaning their difference is within the allowed tolerance. When this happens, the passed test count is increased by 1. This example tests that the current calculation handles invalid input correctly. When the function is given 120 volts and 0 ohms of resistance, it should raise a value error because resistance must be positive. The test catches that expected error and counts it as a pass. The test summary includes the exception case and the total count, then reports how many tests passed overall. It confirms that 120 volts across 60 ohms gives a current of 2 amperes and that 12 volts with 3 amperes gives 36 watts of power. It also confirms that trying to calculate current with 0 resistance correctly raises a value error, showing that the error handling works. This script tests 2 basic electrical calculation functions. One finds current by dividing voltage by resistance and rejects 0 or negative resistance, while the other finds power by multiplying voltage and current and requires non-negative inputs. The tests compare results against expected values, such as 2 amperes for 120 volts and 60 ohms, and 36 watts for 12 volts and 3 amperes. They also confirm that 0 resistance correctly raises a value error, and the script reports which tests pass. Expected results. Expected results give function tests a clear benchmark before a script is used in real engineering work. For simple calculations, such as power or resistance, testers should compare the function's output with known results from hand calculations or trusted software. The aim is not to test every possible input, but to confirm the function behaves correctly in typical cases. If the output does not match the expected result, the calculations or assumptions should be reviewed before moving to more complex problems. Tests for engineering functions should use expected results that are both precise and realistic. Many errors appear as subtle inaccuracies, such as unit conversion mistakes or rounding problems, rather than obvious failures. Checking known conversions, like milliamps to amps, or predictable voltage drop cases, helps catch these issues and encourages learners to verify results instead of blindly trusting script output. Expected results make tests clear by defining what a function is supposed to do. They help others understand the intended behavior of a script and catch problems when code changes. Even simple tests, such as checking conversions or sensor readings, turn assumptions into reliable checks and make engineering scripts easier to maintain. Python code. Expected results. Expected results make engineering tests more concrete by showing what a correct script should produce. Simple known cases help reveal calculation mistakes, and passing tests build confidence in the script. This function calculates electrical power using voltage and current. It first checks that both inputs are non-negative and raises an error if either one is invalid. When the inputs are valid, it returns the power by multiplying voltage by current. The code validates the voltage and current inputs by checking that neither is negative. If either value is below 0, it raises an error, preventing invalid electrical values from being used. The function raises an error if the voltage or current is negative, because those values are invalid for this power calculation. This stops the calculation from continuing with bad input and helps keep the result reliable. This line calculates electrical power by multiplying voltage by current, following the rule that power equals voltage times current. The function then returns that calculated power as its output. The milliamps to amps function converts current from milliamps into amps. It takes one input value in milliamps and divides it by 1,000, giving the equivalent current in amps for standard calculations or comparisons. The current is converted from milliamps to amps by dividing it by 1000. This puts the value in the standard unit used for electrical calculations and comparisons. We create a list of test cases to check whether functions work correctly. Each test case includes a name, a function being tested, its inputs, and the expected result. This makes it easier to test different scenarios systematically and confirm that the functions are reliable. Two tests check the calculate power watts function. One verifies that 12 volts at 2 amps gives 24 watts for a small load. The other verifies that 120 volts with 0 amps gives 0 watts, confirming the function handles 0 current correctly. This test case checks a current conversion function by converting 250 milliamps into amps. The expected result is 0.25 amps, confirming that the function handles a typical input correctly. Initialize the past test count to 0, so it starts fresh before any tests run. This count tracks how many test cases complete successfully during execution. We go through each test case, identify the test name, the function being checked, its inputs, and the expected result. Then we run the function with those inputs and compare the actual output with what was expected. This provides a systematic way to confirm that each function works correctly. The code runs the selected function using the provided inputs and stores the result. This result is then used to check whether the function's output matches the expected answer in the test case. To compare floating point results, we check whether the absolute difference between the actual and expected values is less than a tiny tolerance, such as 1 × 10⁻⁹. This allows for small precision errors, so insignificant differences do not cause a test to fail. The code updates the number of past tests by treating the test result as an integer. In Python, true counts as 1 and false counts as 0, so adding the result to the counter automatically increases it only when a test passes. This line prints a brief summary for each test case, including the test name, expected result, actual result, and pass or fail status. The status is based on comparing the actual and expected results, with a small allowance for decimal differences. This makes it easy to check whether the function works correctly in each scenario. This example shows how to test that an expected error is raised. It calls the power in watts calculation with a negative voltage, which should be rejected and trigger a value error. If the error occurs, the test is marked as passed. If it does not, the test fails because the invalid input was not handled correctly. The code tests whether the power calculation function correctly rejects negative inputs by passing a negative voltage with a positive current. Since negative voltage or current is not allowed, the function should raise an exception. If the exception occurs, the test is considered passed. If it does not, the test fails because the invalid input was not caught. This code handles a specific error when an invalid value is encountered. By catching that error, it confirms the function responds correctly to bad input and helps keep the program robust. This line marks the negative input test as passed. It confirms that invalid input correctly caused an exception, showing the function handles that case as expected. The code reports whether an expected error test passed. It checks that the calculate power watts function raises a value error when given a negative voltage, confirming that the function's error handling works as intended. The code reports how many tests passed out of the total test cases. This gives a quick snapshot of the script's reliability by showing the share of successful tests. The script defines two simple electrical helper functions. One calculates power from voltage and current, and the other converts milliamps to amps. It runs tests for normal cases, zero current, an accurate unit conversion, then reports whether each result matches the expected value. It also checks that negative voltage correctly raises an error, and ends with a summary of how many tests passed. Expected results. Expected results define what correct behavior looks like before a function is used in real engineering work. When testing functions that convert units or calculate values such as voltage drop or power, compare the output with a trusted result from a hand calculation, reliable calculator, or manufacturer data. The goal is to confirm the function works for important known cases rather than trying to test every possible input. When testing engineering scripts, choose expected results that can be checked independently because a test is only as reliable as those values. Do not use the same possibly flawed logic to create both the function and the expected answer, or errors may go unnoticed. Use simple, relevant cases with familiar resistance values, realistic current scenarios, and important boundary conditions such as zero load or minimum voltage. Clear expected results make scripts easier to maintain as projects grow. When a function suddenly returns a different value, it can reveal either an intentional update or an accidental mistake. Simple tests that document expected outcomes help engineers keep calculations reliable, which is especially important when scripts affect safety, equipment sizing, and cost decisions. Python code. Expected results. Expected results make engineering tests reliable. Simple cases should be easy to verify independently, and passing tests help protect future changes to scripts. We define a kilowatts to watts function to convert a power value from kilowatts into watts. It takes the kilowatt value as its input, making the conversion simple and ready for later calculations or checks. The code first checks whether the power value is negative, since negative power is not valid in this context. If it is below zero, the function raises an error to prevent invalid calculations. This helps ensure the function only works with meaningful, non-negative power values. This step converts kilowatts to watts by multiplying the kilowatt value by 1000. It then returns the resulting wattage for later use or verification. The voltage drop function calculates the voltage drop across a resistor using current in amperes and resistance in ohms. It first rejects negative inputs by raising an error, since current and resistance must be non-negative. It then applies Ohm's law by returning the product of current and resistance. The code checks that both current and resistance are non-negative before calculating voltage drop. If either value is below zero, it raises an error explaining that the inputs must be non-negative. This prevents invalid values from being used in the calculation. This calculation uses Ohm's law to find the voltage drop across a component. It multiplies the current in amperes by the resistance in ohms, so the function returns the correct voltage drop value. A list of test cases is created to check whether the functions work correctly. Each test case includes a short description, the function being tested, its input arguments, and the expected result. This structure makes it easy to verify the kilowatts to watts function and the voltage drop function across different conditions. Start by setting the past test count to 0 so the total begins fresh. Each time a test succeeds, increase this count, making it easy to report how many tests passed overall. We loop through each stored test case, take out its name, target function, input arguments, and expected result, then run the function with those arguments. By comparing the actual output with the expected result, we can check that each function works correctly. The code runs a stored function using the provided tuple of inputs. The return value is saved as the actual result, which can then be compared with the expected result to decide whether the test passes. The test compares the function's actual result with the expected result. If they match, the test passes, and that success is recorded. The code counts past tests by converting each pass result from a Boolean into an integer. A true value becomes 1, and a false value becomes 0, so the count increases only when a test passes. This provides a simple and efficient way to tally successful tests. This line gives a quick summary of each test by showing the test name, the expected result, the actual result, and whether it passed. It helps confirm at a glance whether the function is working as intended. The code creates and prints a short test summary showing how many tests passed out of the total. It uses a formatted string to insert the current counts, giving a quick console overview of the results. This script defines two basic calculation functions. One converts kilowatts to watts, and the other finds voltage drop using Ohm's law. It then runs tests that compare each function's output with the expected result, reports whether each test passed, and counts the successful cases. At the end, it summarizes the total passed tests, helping confirm that future code changes do not break existing behavior. In this lecture, you learn to validate user inputs to prevent invalid electrical quantities from corrupting calculations, use exception handling to manage conversion errors, missing files, and impossible operations, and create simple test cases that confirm engineering functions return expected results. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.